Over the past few weeks, we've introduced different relationships that allow us to derive equations of motion for mechanical systems made up of particles. And again, particles, point masses, whatever you want to call them, they have a mass, but they don't have an area, right? So they're infinitesimally small. This week, I'm going to show you how we can use these same relationships, but for rigid bodies. And as you'll see, that does require some adjustment of these equations. And so again, a rigid body has both a mass and has an area. And so to quickly review, for a particle, the force linear momentum relationship is as follows. Let's call that Lm. We have the force acting on the particle is equal to the mass of that particle times the acceleration of that particle in frame A. And the torque angular momentum equation is equal to the following. We have torque of particle P about Q is equal to the derivative of angular momentum plus we have our velocity of point Q in frame A crossed with the linear momentum of P in frame A. Now when we have a rigid body, first of all, we can consider this rigid body, say something that looks like that, as a collection of particles. So we can put a bunch of particles together, and that's a reasonable model for a rigid body. All right, you get the picture there. And so what that means is that now, instead of just writing these two equations for one particle, and we've kind of implicitly done that, is that if you have more than one particle, you can say that for each particle, Pi, and then you can put a subscript here. I, this is mass I, and I. And then you can sum up these equations for all of the particles in your rigid body, and then ultimately what you get is the following. So our force linear momentum equation becomes F, and then I'm going to use this superscript B to stand for rigid body. So the total force acting on our rigid body B is equal to the mass of that rigid body times the acceleration of the center of mass of that rigid body. And that I'm going to call CB. Sometimes I will also just refer to it as C, but C or CB, that means the center of mass of that body. And so this equation is actually very straightforward to use. The next equation, right, again, if you're summing up the total torque that's acting on the rigid body, so here, this is a T, so the torque B, again about some point Q, is equal to, again, the derivative of the angular momentum of our body about Q plus velocity of Q times the linear momentum of our body B in frame A. Now this equation is less straightforward to use, and what you'll see in the next few slides is that we can actually simplify this so that we can use it efficiently and ultimately be able to derive equations of motion for rigid bodies, or systems that consist of rigid bodies. One thing I want to note here is you might notice a difference in the terms or the notation for, say, force, right? So when we're dealing with a particle, that the F was a lowercase f. When we're dealing with a rigid body, we use a capital F. And so that's going to be quite consistent so that we can differentiate whether we're referring to, again, a particle or a rigid body. So for rigid body, you'll see here we also have a capital T for torque of a rigid body, and a capital H for angular momentum, and a capital P for linear momentum. So as I mentioned, the torque angular momentum relationship in this form is not particularly easy to use. However, we can simplify this equation. I'm going to show you 3 different ways in which you can simplify it. The first is when you set Q, so the point that we're taking the torque about, Q equal to the center of mass of the rigid body. And when you do that, now the torque about your center of mass is equal to I. This I here is the mass moment of inertia, or sometimes just called the moment of inertia. In this case, we have the moment of inertia of our rigid body about its center of mass times the angular acceleration of our rigid body in frame A. And so if you're assigning, and usually you do assign a reference frame to your rigid body, because a rigid body, unlike a particle, can rotate, then this is the frame in which is assigned to your rigid body. And we'll review that when we go through some examples. Now, the second way you can simplify this is by setting Q equal to ICR, and that stands for the instantaneous center of rotation. Okay, ICR. And this is the point on the rigid body which is instantaneously at rest with respect to frame A. So for example, let's say we have a rotating rod, right? This point here, even though this rigid body is rotating, this point doesn't rotate with respect to a inertial frame, right? So if we draw our A frame here, or even if we drew our frame here, that point, or that pivot point, doesn't rotate, right? So that would be an example of an instantaneous center of rotation. And if that's the case, then we can write the torque of our rigid body B about ICR. And I put the parentheses here to emphasize that this is a single point, we're just calling it ICR, is equal to the mass moment of inertia of our rigid body about that instantaneous center of rotation. And then that's again multiplied by the acceleration of our angular acceleration of our rigid body in frame A. And lastly, we have perhaps what is the most general form when Q is, I'm going to say, just some point that you've decided. If that's the case, we get torque, and we're just going to keep calling that about point Q, is equal to the moment of inertia of our rigid body about its center of mass, again times the angular acceleration of our rigid body in frame A. But then you also have this additional term, and so the plus, and now here you have the position vector that takes you from point Q to the rigid body, CB, crossed with the mass of our rigid body times the acceleration of the center of mass of our rigid body in frame A. So now that we've defined the three forms of the torque equation that you can use, you might be asking yourself, how do I know which one I should be using for a given problem? And so here's my advice. If you have a rigid body that's pivoting about a point or has a hinge, in other words, if you have a problem where it's very clear where the instantaneous center of rotation is, I would use this equation here. However, if you're unsure where that center of rotation is, I would, or for any other case, I would generally recommend that you use this form. Right? This setting Q equal to the center of mass, this is like your workhorse. It will always be simple and correct. So when in doubt, I would use this method here. Now, taking Q with respect to some other point, you may want to use that in some circumstance, in some special case, but honestly, this will probably be the least common. Right? And you can imagine that it's, you don't want to calculate this if you don't have to, additional term. So generally, if you can use one of the other two methods, it's just preferred because there's going to be less algebra involved. And so to summarize, for rigid bodies, our force linear momentum relationship that we will use is force of our rigid body is equal to the mass of the body times the acceleration of the center mass of our body in frame A. And then our torque angular momentum relationship will simplify such that we can use one of the three following equations. Torque of our body about the center of mass is equal to, again, the moment of inertia of the body about the center of mass times the angular acceleration of our body in frame A. The torque of our rigid body about its instantaneous center of rotation, again equal to the moment of inertia of our body with respect to that instantaneous center of rotation, again multiplied by the angular acceleration. And then lastly, our most general form. So we have the torque of our body about some point Q, which is going to equal the moment of inertia of our body about its center of mass times the angular acceleration of the body in frame A, plus our additional term R Q to the center of mass crossed with the mass of our body times the acceleration of the center of mass in frame A. And in the subsequent videos, I'll review how to calculate the mass moment of inertia, as well as show you how we can then use these equations here to derive equations of motion for systems with rigid bodies.